Hello friends, welcome to my channel. This is Thermodynamics and Power Plant Isro question paper from 2002 to 2016 part 3. The question is, the specific heat of diatomic gas at constant pressure is given by R equal to universal gas constant and M equal to molecular weight of gas. So here R is universal gas constant. Gas constant. We know Rc is our characteristic gas constant. Rc is equal to universal gas constant by molecular weight. And one more thing, Cp minus Cv equal to Rc. This is characteristic constant. Divide Cp both sides. Cp by Cv minus 1 by Cp by Cv and Rc by Cp. So 1 minus 1 by gamma Rc by Cp. So gamma minus 1 by gamma Rc by Cp. Then Cp equal to gamma into characteristic gas constant divided by gamma minus 1. Then this is equation 1 and this is equation 2. And one more thing we know, gamma value for diatomic gas equal to 7 by 5. So this one also we will use here. These three things we already discussed. So Cp equal to, it's 7 by 5 into Rc by 7 by 5 minus 1. So 7 by 5 Rc by 7 minus 5 by 5. So it's 7 by 5 into 5 by 2 into Rc. 5 cancel. It's 7 by 2 characteristic gas constant. Then put this one. In place of Rc, 7 by 2 universal gas constant by molecular weight, Cp equal to this one. In this question, this one they asked. So from option, Cp equal to 7 by 2 universal gas constant by molecular constant. Molecular weight. Kinetic energy of the molecules in terms of absolute temperature T is proportional to how much? We know kinetic energy equal to 3 by 2 K into T. K is our Boyle's constant and T is our absolute temperature. Absolute temperature. So kinetic energy is proportional to T. From option A is our answer. The relation Pv to the power gamma equal to constant, where gamma is the ratio of specific heats of ideal gas, is applicable to what? Pv to the power gamma equal to constant and Cp by Cv equal to gamma. It's applicable to any adiabatic process? No. Only reversible adiabatic process is. This is the answer. B is the answer. Across a normal shock, first I will draw the diagram of normal shock. This is a divergent passage. Fluid is flowing like this from this end to this end. and inlet is supersonic flow, Mach number is greater than 1, and after the shock wave at outlet the flow is subsonic, Mach number is less than 1. So this is shock wave. This is shock waves. Inlet is supersonic and outlet is subsonic. Here properties are velocity, then pressure at inlet, and enthalpy before the shock. These are before the shock. Enthalpy and density and entropy. And after the shock, it's V2, P2, H2, ρ2 and S2. Here pressure, temperature, then density, then entropy. These properties, they are increasing after the shock. Stagnation pressure, velocity, Mach number, they will decrease after the shock. And stagnation temperature is constant or static temperature. PO and TO, they are stagnation or static pressure and static temperature. So in this question, across a normal shock, static pressure and static temperature rises, static pressure is decreases, and static temperature is constant. So A is not possible. B, entropy remains constant, entropy increases, so B is also not possible. Velocity and static pressure decreases, velocity this one and static pressure PO, this is decreases, so C is our answer. Density and temperature decreases, density increases, temperature both are increases, so D also not possible. C is our answer. This is very, very important for IAS examination. The critical point and triple point data for water are TC is equal to 374 degrees Celsius and PC equal to 22.1 megapascal. Triple point temperature equal to 0.01 degree Celsius and triple point pressure equal to 0.6 kilopascal. Indicate the phase change that will occur in the following cases. Ice at 0.5 kilopascal is heated isobarically or constant pressure heating. Then double I, water vapor at 400 degrees Celsius is compressed isothermally. This is our critical point and this is our triple point. First is water is heated isobarically, so PT diagram. This is our sublimation line and this is our vaporization line and this is our fusion line. So in this question A, B, it's here from solid to vapor and here it's liquid. Here this is critical point and this is triple point. This is our C to D. So ice at 0.5 kPa is heated isobarically. It's AB, constant pressure heating. Then water vapor at 400 degrees Celsius is compressed isothermally. It's along C to D. So A is our answer. The ratio of specific heats of a gas is 1.4 and the value of specific heat at constant pressure is 7 calorie per mole degree Celsius. The difference between specific heat at constant pressure and specific heat at constant volume will be how much in calorie per mole degree Celsius? We know Cp by Cv is gamma. Ratio of specific heats, its value given 1.4 and specific heat at constant pressure Cp is 7 calorie per mole degree Celsius. We know Cp minus Cv equal to characteristic gas constant R. So divide Cp both sides. Cp by Cp minus Cv by Cp, this one already discussed, R by Cp. So 1 minus 1 by gamma R by Cp. So Cp equal to gamma into R by gamma minus 1. Here we will put the value of gamma and Cp, then we will get R value. We have to calculate this one, R value. So R equal to Cp into gamma minus 1 by gamma. Put the values of Cp and gamma. R equal to Cp is 7, gamma is 1.4 minus 1 divided by 1.4. So it's 7 into 0.4 by 1.4. So it's 7 into 4 by 14. 2, 4, it's 2. R equal to 2. From option, it's 2 calorie per mole degree Celsius. Option D is our answer. Question is, for one-dimensional isentropic flow in a diverging passage, if the initial static pressure is P1 and the initial Mach number is M1 and M1 is less than 1 means subsonic, then for the downstream flow Mach number relation and pressure relation we have to calculate. So it's a diverging passage. And inlet is subsonic, less than 1. So it's a divergent. It will act as diffuser. So it's a case of subsonic diffuser or supersonic nozzle. Both case outlet will be same. Pressure will increase and our velocity will decrease. So velocity will decrease means, so velocity decreases means inlet Mach number M1 is greater than M2. Here M1 and M2, P1, P2, and pressure increases means P2 is greater than P1. So from option C is our answer. Fluid is flowing like this. In this case, we can use another method for diverging passage. Here inlet and outlet. M is less than 1. This is M1, M2, P1, P2. We can use this relation dA by A equal to dV by V m square minus 1. Here already given m is less than 1 means subsonic, so this term will negative, and area is increasing, so this term dA by A, this term is positive and this m square minus 1 is negative, so dB by V into m square minus 1 should positive, so dB by V is negative, negative is final positive. dB by V negative means V2 minus V1 is negative, so V1 is greater than V2, so M1 is greater than M2, so this one we can get. Same, C is our answer. In the van der Waals gas equation, P plus A by V square whole into V minus B equal to R2. The constant A is introduced to compensate for cohesion force or intermolecular forces. B is our answer. Here in van der Waals gas equation, P is our real gas pressure, A and B are constants, V is real gas volume, and R is characteristic gas constant, T is our absolute temperature. The term P plus A by V square, its ideal gas pressure, and the term V minus B is ideal gas volume. Ideal gas volume, and A for compensation of force of cohesion or intermolecular forces. Intermolecular forces, and B uses for volume, compensation of volume. Sometimes B also they are asking in IAS examination. A, B both are important. Air with initial condition of P1 V1 expands to final condition P1 by 2 and 3 V1. The process is what? PV diagram we will draw. Two process we will do for this question. At initial condition or 1, here its pressure is P1 and volume is V1 in this PV diagram, and then second case P1 by 2, it's P1 by 2 pressure and 3 V1 volume from here to here, 1 to 2. And we know for isothermal process P1 V1 equal to P2 V2, N equal to 1 in isothermal case. So P1 V1 equal to P2 is P1 by 2 and V2 is 3 V1. So only we will change the pressure. P1 V1 equal to, this is P1 by 2 into 3 V1, only V1, V2. So V2 we have to calculate, it's 2 V1, here it will come like this when N equal to 1. this side n equal to 0, this side n equal to infinity. So this one n is less than 1. From option D is our answer. Here again I am repeating this term. P1 V1 by T1 equal to P2 V2 by T2. Isothermal, so T cancel. N equal to 1 isothermal case. If P1 is reducing by 2, then V2 should increase by 2 times. This one we will put here. We will get n is less than. Here before doing method 2, we should remember the two terms, ln2 and ln half, ln3 and ln 1 by 3. This is very useful. 0.69 and minus 0.69, 1.098 and minus 1.098. So here P1 V1 to the power n equal to P2 V2 to the power n. P2 equal to P1 by 2 and V2 equal to 3 V1. So in this equation we will put P2 by P1 equal to V1 V2 whole to the power n. Take logarithm n into ln V1 by V2. So n equal to P2 by P1 by ln V1 by V2. So ln P2 is P1 by 2 divided by P1 ln V2 is 3 V1. 3 V1. P1 cancel. So ln 1 by 2 by ln 1 by 3. From here ln2 and ln3 we have to remember. For ln half it will minus and ln 1 by 3, ln3 will be minus. So ln half is minus 0.69 and here ln 1 by 3 is minus 1.098. So it will come around 0.48, which is less than 1. N is less than 1. So from option polytropic with n is less than 1, D is our answer. Method 1 and method 2 will get same answer. Polytropic index n is given by how much? Polytropic process. P V to the power n is constant. So P1 V1 to the power n equal to P2 V2 to the power n. So P2 by P1 equal to V1 to the power V2, V1 by V2 whole to the power n. So n equal to log P2 by P1 divided by log V1 by V2. From option log P2 by P1 divided by log V1 by V2. A is our answer. Thank you friends. Thank you for watching my video.